Hi, my name's James Doherty. I'm a Senior Lecturer in Geotechnical Engineering at the University of Western Australia, and I've developed a web-based application for the lateral analysis of piles, which goes by the name of LAP. In this video, which is the second in a series introducing LAP, I will demonstrate how to set up and analyse a model that includes two different pile sections along with two different soil layers. So we'll have clay overlying sand. And we'll also subject the pile to a prescribed displacement at the top, as well as a boundary condition that prevents rotation of the pile head. So it'll be like a fixed head condition. The application can be accessed at www.geocalcs.com/lap, so we'll go straight there. If you haven't already done so, you can register simply by clicking on the Register tab and filling in those forms. Once you've done that, you go back and enter your email address and your password to access the program. To create a new project in LAP, you select the Create New Project option, and then you enter a project name. In this case, we'll just enter Example Project as the project name and Run 1 as the Run ID, and then hit the Create button. As soon as you hit the Create button, the Pile menu is active. So to define the pile, you've defined the elevation of the top of the pile and you define the total length. So the elevation of the top of the pile in this model is 2 meters and the total pile length is 17 meters. Once you do that, you get this clickable object that when you select, you get some menu items on the left that allow you to enter the properties. The properties for this pile will enter as 1.3 for the diameter and the flexural rigidity, so the EI value of 50,000 kilonewton meters squared. In this particular model, we want to create two pile sections. So we create the second section by hitting the plus button, and then we enter the elevation of the top of the second section. So that then splits our clickable object into two parts, the top representing section 1 and the bottom representing section 2. And then we enter the properties for the second section of the pile. We enter a flexural rigidity of 25,000 and a plastic moment capacity of 1,000 kilonewton meters, fairly arbitrary values. We then move on to define the soil, and the first thing we do is define the elevation of the ground surface, and in this case we enter that as 1, and once we do that we get this clickable object representing the soil. We start entering properties that represent the soil, so in this case we're going to enter 16 as the total unit weight for this particular soil layer. From the type we select clay API from our list of available PY models, and we're going to choose the consistency as soft. From that list there, we'll select static as the analysis type, and then we'll enter the undrained shear strength at the top and then the change in undrained shear strength with depth. Again, in this model we have two soil layers, so hit the plus button and then enter the elevation of the second soil layer as -5 meters. That splits our soil up into two clickable objects. We can change the color of the second object just to give us a bit of contrast. And then we start entering properties for that second section, 18 kilonewtons per meter for the unit weight. I'm going to select Sand API and give it 35 degrees as friction angle. Then we can select the groundwater table and enter that as 1.5. Then we get the symbol representing the groundwater in our clickable objects. Next we define the loads, and we have the option of including a surcharge, which it has the effect of increasing the vertical stress in the soil by the amount you enter. In this particular model, we're not going to include a surcharge, so we just set that value to 0. To define the first load on the pile, we select load 1, and then from the pull down menu, we select prescribed displacement, and then we enter the elevation where we want to prescribe that displacement, and that is 2 meters at the top of the pile, and the value we're going to prescribe is 1 meter. To create a second load, we hit the plus button, and then we select from the pull down menu a prescribed rotation, and we want to fix the pile head at the top, so enter the elevation at the top of the pile and then enter 0 as the prescribed rotation. After doing that, we end up with these two clickable objects in our model representing our prescribed displacement and rotation. LAP also gives you the option of entering elastic reaction springs. These are meant to represent ties or struts. They're not used to represent the soil. In this particular model, we don't have any, so we don't need to include them. We've now defined everything, so we can run the model by hitting the green button in the upper right-hand corner. And when we do that, we get a series of summary plots. First is the load displacement plot, which shows we get a displacement of 1 meter, which with a force of about 900 or so kilonewtons. We get a bending moment diagram, a pile deflection diagram, a shear force diagram, and also a pressure profile diagram. We can download a full set of results to Excel, and when you do that, you'll see an Excel sheet with a series of tabs. The first tab basically summarizes the model, including the project name, the run ID, your solution settings, etc. We then have a summary results tab, which just gives you some information about the time steps used to solve the problem, the number of iterations in each time step, etc. Next, we have a load deformation tab, and this tab provides the displacement and force or the rotation and moment for each of the load cases that we specified. So our first load case was a prescribed displacement of 1 meter, and they are the reaction forces that we needed to generate that displacement. Similarly, we have zero rotation and the moments required to generate that zero rotation. Then we have results that summarize our pile. So these are our elevation coordinates, our diameter, the pile EI. Note we have two different pile sections, and you can see that the properties change at an elevation of -2 meters. Along with that, we have bending moments for each of the time steps, shear forces for each of the time steps, displacements, and also rotations within the pile. And of course, you can quite simply just plot the elevation, for example, against pile bending moment, the pile bending moment at the end of the analysis. In Excel, it's fairly straightforward. So just altering the axes, so we plot elevation on the vertical axis and bending moment on the horizontal axis. That's the bending moment diagram that we get. Then we move over to soil springs, and again you can see the elevation of each soil spring and the input properties used to generate the PY curve for that particular spring, and we have a clay model overlying a sand model, so the parameters are different. Then we also, at each spring, we output the Y value versus the P value, so you can actually plot the PY curve for each of your springs. Excel doesn't naturally plot these values in a very convenient way, so you just, once you plot them, you just have to reselect the vertical and horizontal axes, and that's your PY curve for the first spring, with your P value in kilonewtons per meter on the vertical axis and Y in meters on the horizontal axis. Whenever you run a project, it's automatically saved to the cloud. So if you go back to projects and load project, you'll see that this job now exists in the jobs list. You have a few options. You can share it, or you can load it back in at another time and modify it and rerun it whenever you like. For more information, you can click on the manual option to see the user manual for LAP. The example that I've been through in this video is more or less based on the first example in the user manual. And if you've got any questions, feel free to email me. My email address is there on the front page of the user manual. I hope you enjoyed the video and I hope you enjoy using LAP.